just filmed like 12 minutes of this and my microphone wasn't plugged in. And I want the microphone plugged in because the AC is on and it's going to be loud if I don't have it plugged in. So we'll start over. Let's just pretend that didn't happen. You're not going to see it, so it didn't happen, right? Welcome to the Patreon video for June, which is about computational physics and also why I don't like Windows machines, which is just a brief little aside, I think. But if you're going to talk about computational physics, I think the easiest way to do that is to write a physics simulation and just do one. So today for this video, we could call it, Baby's First Physics Simulation. We're going to do my favorite, my classic physics demonstration. Hang on, I got one here. We'll do a bouncing ball. Okay, so we will write a physics simulation to predict what will happen if we drop this ball and hit a hard surface like the earth or this desk in front of me. How would you go about doing that? Let's do it together. Also, I have switched up my camera, so I don't know if I'm looking. Am I looking at you? Is there or there? Let me know how this is. The first thing you need when you're writing a physics simulation are equations of motion. Like, what is going to happen to this ball when I drop it? What forces are on this object? The first is like gravity, right? I drop a ball, it's going to fall down. That's simple. That's easy. We know that as it falls, it is going to accelerate due to gravity. There's a gravitational acceleration. So if the velocity starts at 0, as it goes down, it will speed up. And we can get from kinematic equations. Man, sometimes I wish I had like a chalkboard. It would be hard to film a chalkboard, but that's how I want it. Like if I was in person, that's how we would just stand next to a chalkboard and do this, but it's fine. But the kinematic equation says that the final velocity will be equal to the initial velocity plus the acceleration of that object times the time. So we could just use this equation of motion to calculate how fast it's going when it's here versus when it's here versus when it's on the ground, you know. The second thing though is that when this ball, because it's a rubber ball, hits the ground, it's not going to just like stop, right? It's not going to break apart. It's not a coffee cup. It's going to bounce back up. So you need to get an equation for the bounce, which is trickier. So I'm going to, again, I wish I had a chalkboard, but I'm going to do it on my tablet. Okay, so there's a specific type of collision called a perfectly elastic collision where things just bounce off of each other and conserve kinetic energy and momentum. Pool balls can be kind of like this. So let's model our system as if the system is perfectly elastic. We know bouncing a ball is not a perfectly elastic collision, right? Because the ball hits the ground, it does not bounce back up to its original height. But let's pretend it does, just for a minute, to try to get to this equation of motion. Okay, so for a perfectly elastic collision, you have that the kinetic energy is going to be constant, so there's no change. And you also have that the momentum is constant, so there's no change. I never know how much detail to give you guys. So this delta just means that you have some final kinetic energy minus some initial kinetic energy, and the change is 0. And it's the same here. This is momentum. P is momentum. So it's P final minus P initial equals 0. Okay, so let's write this out. If you take this equation that's like KE final minus KE initial equals 0, what you can actually write is KE final equals KE initial. But I always think of it in terms of a collision as like before equals after. So let's do it like that. So for kinetic energy, you have 1/2 the mass of the ball times the velocity of the ball squared, the initial velocity of the ball. So I'll put VB1 plus 1/2 the mass of the earth times the initial velocity of the earth, VE1 squared, is equal to 1/2 mb VB2, so the final velocity of the ball, plus 1/2 me VE squared, VE2 squared. So you can cancel out the 1/2s, and let's arrange it so that the ball is on one side and the earth is on the other side. So you get mb times VB1 squared minus VB2 squared is equal to me times ve2 squared minus ve1 squared. And let's multiply this out, so you get mb times vb1 minus vb2 times vb1 plus vb2 is equal to me times ve2 minus ve1 times ve2 plus ve1. Okay, we'll call this equation 1. Now let's look at our conservation of momentum, which will say that the mass of the ball times the initial velocity of the ball, v1, plus the mass of the earth times the initial velocity of the earth is equal to the mass of the ball times the final velocity of the ball plus the mass of the earth times the final velocity of the earth. Let's rearrange this so the balls are on one side. So we get mb times vb1 minus vb2 is equal to me times ve2 minus ve1. And we'll call this equation 2. If we take equation 1 and divide it by equation 2, we get something very simple, which is vb1 plus vb2 is equal to ve2 plus ve1. Okay, now let's rearrange this so all of our befores, before the collision, so our v1s are equal to all of our afters, our v2s. So we get vb1 minus ve1 is equal to ve2 minus vb2. And here I want to remove this negative sign, pull it out so that vb2 can be first. So we get vb1 minus ve1 is equal to negative vb2 minus ve2. Okay, so now what I want to do is think about our problem again. So this is true for a perfectly elastic collision where kinetic energy and momentum are conserved. In our case, we know that that's not true because the ball will bounce up to a lower height and eventually it will stop bouncing. So the energy has to be going into the collision. However, for our perfectly elastic collision, if we think we have a ball bouncing off the earth, how much will that tiny rubber ball change the velocity of the earth? 0, right? So we can just set the initial and final velocity of the earths to 0. So you get that the initial velocity of the ball is equal to the negative of the velocity. This makes sense for our elastic collision. If no energy is lost in the collision, the ball will hit the ground and will bounce back to the same height. We know it doesn't do that. So in this case, where the initial velocity or the negative of the initial velocity divided by the final velocity is equal to 1, we know that that can't be the case for our ball. So instead, we set this equal to some constant. This is called the coefficient of restitution. What this actually means is that you have some new final velocity. It is going to be equal to the negative of this coefficient times your initial velocity. And that makes sense. This is going to be like a fraction, somewhere between 0 and 1, right? So your ball hits the ground, it will bounce up with the reverse sign of velocity because it's going to be moving up instead of down, but it's just going to be a fraction of what the initial velocity was. So eventually this will just go to 0 and the ball will stop bouncing. That's what we expect to happen. So if we were to plot this ball's motion, so we have some kind of time on the x-axis and height on the y-axis, what's going to happen is as it falls, it's going to go like this. It's going to hit the ground. It's going to bounce back up. It's going to hit the ground. It's going to bounce back up to less until eventually that. So according to this equation of motion and also our original like v equals v initial plus at, these two equations of motion, if we were to model what a bouncing ball will do in a simulation, we should get something like this. So, let's write that simulation. Okay, this is going to be a really vulnerable moment for me where I show you some code I've written. Now listen, I am not like a professional coder. Physicist code in like the most utilitarian way possible. So if it works and it's fine. And for something like this, I would never like optimize it or anything. So it's very simple. It's very bare bones. Just like, it's fine. It's gonna work. It's totally fine. Okay. So let's go through this code. This is a physics simulation code. Okay. So I'm just doing this in Python. Oh, and my down key doesn't work. So that's normal. So here I have defined a function that will calculate the bounce evolution. So what it's going to ask for is your initial height, your initial velocity, your coefficient of restitution for your ball, and the amount of time you run the simulation for. So obviously I've been talking about dropping a ball, but if you throw it down towards the ground, that's going to also affect the simulation. And the reason I chose a bouncing ball was because of this coefficient of restitution. There's something interesting there. That is a experimentally derived quantity, right? That depends on the hardness of your material, the hardness of the surface you're dropping it on, the angle of the bounce, all kinds of things. Like I said, it would be somewhere between 0 and 1, and that's true. But what it is will depend on all of those properties of the ball and the bounce and the collision. And that's the thing about physics simulations, is it's not just, equations of motion. Okay. So here we define G as 9.81. This is actually another experimentally verified quantity, right? I could calculate what G is, right? Because you know Newton's law of gravity, F is equal to G, a constant, which is an experimentally derived quantity. So I guess I would have to use that, times the mass of the object times the mass of the Earth, over r squared, right? So G at any location is just these numbers. And for most of us, it's like 9.81. Another parameter here is delta t, which is the time step. So the thing about physics simulations is that they are not like the real world, right? So what you do is you place your particle at a position and you say, I am going to move it forward. Like in this case, I said 0.01 seconds. And you plug dt, 0.01 seconds, into your equations of motion, and you're like, if that amount of time passed and nothing changed, my ball is now here. And then you do it again, and you're like, 0.01 seconds, now it's here. And so you're not calculating how the ball is actually moving. You're calculating how it will move in that time step, moving it, and then calculating how it will move in that time step again. And then we have this simple loop for while the time is lower than the time I put, I am going to, well, let's go by step by step. So first, if the ball goes below 0, meaning it hits the ground, there's no actual ground in the simulation. I've just defined 0 to be the ground. What it will do is it will use that equation we just derived-ish, where it's got the new velocity will equal the old velocity times that coefficient of restitution times the negative. So if it was going down at some velocity, it will now be going back up with a lower velocity. And then we account for the change in velocity due to gravitational acceleration. So while it's falling, it's going to speed up. While it's bouncing back up, it will slow down until it reaches some 0 point, and then it will start falling again. All that good stuff. And then the last part here is I calculate how that velocity will change the position of the particle, and I move the particle. And that's it. That's the whole thing. So what this simulation does is it asks you for an initial position and an initial velocity and for the property of your material, and it just evolves this in time. So what I've done here is I've set up a bounce to start. Notice there are no units in here. Since I have gravity as 9.81, that means my units are in meters per second. So this means this is at 0.01 seconds. And this means if I type 20 right here, it is going to be 20 meters off the ground. I'm starting it with a 0 velocity. I'm starting it with a coefficient of restitution of 0.85, and I want to run this simulation for 25 seconds. So let's see what it looks like. Yay! So there we did it. We ran a physics simulation. We calculated the trajectory of a ball that is dropped from a height of 20 meters with a coefficient of restitution of 0.85. So it goes like this. And then eventually it just stops bouncing. We did it. So if I asked you, I dropped this ball from this height, it has this coefficient of restitution, how many bounces would it do? You could use this physics simulation to figure it out. So what I'm doing now is I'm adding a second simulation. So here I've got y2, which will be my second bounce, where I'm dropping it from the same height, but this time my coefficient is set to 1. So let me just make sure it's the same time. So we can see how this changes the evolution. So we'll run it again. And here we have two simulations, one with a coefficient of 1, which is this orange dashed line, and one with a coefficient of 0.85. And you can see when you set this to 1, the ball just bounces to the same height. It doesn't seem to be losing any energy in the collision. This is a perfectly elastic situation, but that's not what balls do. What balls do is actually this. Okay, so now what I've done is I've changed the second simulation so that it has a coefficient of restitution of 0.75. So that's lower than 0.85, which means that it should do less bounces. Let's see. Nice. So for this orange line now, the coefficient of restitution is 0.75. You can see it bounces one time and then it doesn't recover. It just stops bouncing. Also, notice that these curves are exactly the same until it bounces. And this makes perfect sense, right? Because right here, the only thing that's happening is gravity is pulling this object toward the earth, right? So it doesn't matter what they're made of, they're gonna fall at the same rate. But once they hit the ground, their properties, their material properties become important. And the ball with the higher coefficient of restitution goes higher and bounces a bunch more times. So there we go. We did a physics simulation. I don't think people think of this when they're doing physics simulations though, so I made another one. So let's see it, hang on. Okay, so you see our little blue line, that's our bouncing ball. What this looks like in physical space is something like this. You drop the ball, it bounces to a lower height than it was dropped from, and eventually it stopped bouncing. So physics simulations are also really great for visualization purposes. Like if you just look at the equations of motion and say how many bounces, you just have to do a bunch of math. But if you're running a simulation like this, you can kind of just look at it. You can kind of just see the resulting evolution. Okay, I'm sure you've been thinking of some problems with that simulation, but that's kind of the fun of simulations, right? You make them as accurate as they have to be to solve the problem. So let's think about some of the inaccuracies we have in that simulation. The first is that we only consider vertical motion, right? We say the ball falls, and that's kind of okay, right? Like if you're falling, gravity doesn't really care what you're doing in the x direction. It's just pulling you down towards the center. So even if it was like a windy day and the ball was like being blown, it would still fall according to like the acceleration due to gravity. So that's okay. But if you do get blown from like your hard concrete that you were going to bounce onto the grass, that's going to affect your coefficient of restitution, which is dependent on the material of the two surfaces, not just the one surface. So this simulation would only work if you fall on the material as prescribed by your coefficient. Another thing is that I dropped the ball from 20 meters, which is pretty high. What is that? That's like 65 feet. So if a floor is 10 floors, say that's like the 6th floor of a building, is that high enough for a ball to reach terminal velocity and then our acceleration due to gravity equation wouldn't work anymore? Probably not. Probably not. We could look this up. That's not the point. The point is to say that my simulation did not limit my height. I could have dropped that ball in the simulation from 2 times 10 to the 8 meters, you know, and my simulation isn't the real world. My simulation would have just calculated it. And that's part of like garbage in, garbage out. When you set your initial conditions for a computer simulation, you need to know that you're doing realistic physics. You need to know the limits of your understanding of your little model. We modeled our collision as like this similar to elastic collision by a little ratio, and we talked about gravity on Earth in a specific location. If we tried to take that simulation and use it elsewhere, it just wouldn't work because we have to know the limits of our physics. I feel like I talk about this a lot on my channel, by the way. Like when you do a simulation wrong, you will get wrong results, and it's up to the user. Like that is a tool. I am the user. I need to know that my results are realistic, are physical, and you kind of need to back that up. So when you run a galaxy simulation, for example, there are all kinds of common standard tests you do. Like you'll run like an isotropic ball of gas with your code to make sure it does the thing you expect it to do. You'll run a disk of stars to make sure it forms a bar. Like we have these standard little tests you do to test your code to make sure your code is physical before you just do a new result. You don't just want to jump in and do something new. So you use your simulation as a tool to answer a question, and you have to make sure it's as accurate as it can be to answer that equation. And so you might say, like, well, why not just take it further? Why not model everything with the exact, like, fundamental rules of physics using fundamental forces? So if you think about a little plastic ball, it's not a ball, right? It's some number of molecules that are stuck together by, like, this strong force, right? Like, what is plastic? It's like polycarbon, like some huge macromolecule. You would model those all clumped together in a ball, and as it bounced toward the earth, you would model the earth as a bunch of atoms and molecules, and they wouldn't hit each other because you put electrodynamics in it, right? Or hydrodynamics into it, right? So the way we modeled it was like the ball hits the ground and bounces away. But in real life, what happens is the ball falls towards the earth falls towards the ball, and they do not hit each other because of the electromagnetic force. The reason the ball doesn't fly right through the earth is on a fundamental level because of quantum mechanics, right? The Pauli exclusion principle says that particles cannot occupy the same quantum number, so spatially they cannot overlap, which means as the ball falls towards the earth, it bounces away due to the electromagnetic force. Quantum mechanics, quantum, right? But that's an impossible thing to simulate. You can't model a ball as more than an Avogadro's number of particles. Like that simulation would never run. That's an impossible task for a computer. And you can't model the Earth as an adequate number of particles because of scaling. So scales are really hard for computers to do. I think I don't know if people are interested when I say this, but I find it very interesting that we've never modeled a star from like cloud to collapse to star, because you can't model that number of particles. You cannot model really small interactions between hydrogen and also enough of those to make up a star. Like we cannot model as many particles as are in the world. So every single simulation is always an approximation. And once you start adding things, you're going to really slow down your simulation. You're increasing the computation time, you're increasing the power required, and you're heating the planet to model something that doesn't really matter. Like our bouncy ball simulation was totally fine. Sure, if we wanted, we could model the Earth's magnetic field in there. Like the ball certainly feels the Earth's magnetic field because it's made up of atoms and molecules, but it's not charged. So the Earth's magnetic field is not going to change the motion, so we just don't need it. So we don't put it in. So you're constantly doing this like little battle of making things as realistic as you need, but not so realistic that it breaks your simulation. So every single simulation is a toy model, like a little version of the story that's enough to get you the answer, but not so much that you could never actually run the simulation. And here's the thing, I have done a video for Patreon about whether simulations are experiment or theory, and I think I waffled and said the middle. In my opinion, simulations are firmly in theory. They take the math that you've been working on in your theory and they just move them forward. And that is all. You can never get new physics out of a simulation. But one of the arguments for theory is that you're never actually physically modeling the entire universe because you just can't. Do you know what I mean? So I have here a little list of bottlenecks of things that you consider when you're writing a simulation, things that might slow you down. The first is the time step. So if you saw on our little bouncy ball simulation, I set it at 0.01 seconds, which is fine because the whole simulation was running for 25 seconds. Okay, so the time step of 0.01 seconds for our bouncy ball simulation means the ball has some velocity. I move it to a position according to where it would be 0.01 seconds later. I recalculate the velocity. I move it to a position based on that velocity where it would be 0.01 seconds later, and I recalculate the velocity again. If I was to increase the time step and say, okay, maybe instead I'll just calculate the velocity every 5 seconds, that would be a problem, right? Because in 5 seconds, acceleration due to gravity will wildly change that ball's velocity. So you're not going to get a really accurate answer. So you have to make it short enough that you're actually catching all the velocity information. However, if you make it too short, so if I set it to like 0.000001 seconds, it's going to stop and redo a calculation all the time, and it's never going to hit the ground. So you're choosing between high accuracy and just like good enough to run the simulation. This becomes really, really important if you think about like orbits. So imagine you're modeling the solar system. You have the sun and you have Mercury right here. It's on a very small orbit. It goes through this orbit very quickly compared to, Pluto way out here. Like Mercury is going to make a bunch of orbits in the time that Pluto does like a little tiny arc over here. So if your time step is really long, you're going to accurately catch Pluto's orbit. But if your time step's really long, you're not going to get Mercury's orbit at all. So you have to decide your time step based on your system, which usually ends up being that you choose the limit, the bottleneck. You have to have your time steps short enough that you resolve Mercury's orbit, so you're calculating Pluto's orbit even though it's barely moving. This goes back to that scale thing I was talking about. You want to resolve your system, which sometimes means you're wasting a lot of time calculating Pluto's orbit even though it doesn't change. And of course, people come up with all sorts of solutions to this. I'm just doing like a broad overview. Like people have solved this problem, but it's fine. Okay, the next thing you can think about is when you're doing a simulation is the number of calculations. So we had 1 point in our simulation. So imagine you're simulating a galaxy, okay? A galaxy has 100 billion stars in it, okay? The gravitational potential of the system is going to depend on the position of every single one of those stars. So if you pick one star and you want to calculate how it's going to accelerate due to gravity, you need to calculate the gravitational potential of all other 100 billion objects, which means you have to do 100 billion calculations. And then when you move to the next star, you have to do it again, 100 billion calculations. So if you're simulating a galaxy, your time step moves, you do 100 billion calculations, and then you move all your particles again, and you do 100 billion calculations. And yeah, maybe that only takes like 45 seconds. But if you're going to do 100 million time steps in your simulation, those 45 seconds add up, right? People who simulate physics are very, very smart. There are tons of ways to solve this problem. One way is by using a tree code where you're like, okay, here's my star. You only need to calculate 1-to-1 forces from like this little circle. And then back here, just approximate all that mass as like 1 point. And like that's good enough to get you where you're going. It's the same exact thing where it's like we could value accuracy or we could value like actually getting a result from the simulation. So there are all kinds of tricks on how to get your gravity calculations to work really nicely, but not actually just being adding up 100 billion calculations, because that's just impossible to do. Another thing people do is instead of doing particles, they'll put their particles on a grid and they're like, okay, we just calculate the mass in this square and we just calculate the potential due to the masses of all these squares, which greatly lowers your number of calculations. So you can have adaptive codes as well that will change the size of the grid. So like in regions where you have a lot of particles interacting, your grid's really small and the accuracy of those results is much higher compared to like outside your galaxy where you don't have that many particles. It doesn't really matter what's going on. So I talked about how your time step can be a problem, like you have to resolve different areas of the simulation. I talked about how the number of calculations can be a problem. So if you want to model a real galaxy with 100 billion stars, you have to do 100 billion gravitational calculations for every star. Although, no one ever actually models 100 billion stars. There's a group that pretends they're doing simulations with 100 billion particles, but they're not. For example, in my PhD thesis, which was like 6 years ago, so it's probably way out of date now, I had 10 million particles in my simulation, and every particle was accounting for 10,000 stars. So each particle represented a system of stars that was 10,000 stars, because that's as accurate as you can get if you actually want your simulation to run in time for you to write a PhD thesis on it. I also could talk about parallelization. That's how you say that. You can have a supercomputer running with 480 nodes. So like you paused your time step to calculate the gravitational potential of all your particles. You can separate that calculation to different nodes so that simultaneously different particles are being calculated at once. The issue there is that you often have to wait for a node to finish, and the bottleneck comes from the communication between the nodes. It's just like, okay, you're calculating the gravitational potential on this side of the galaxy and this side of the galaxy, but you need this information over here. So you can't just like infinitely parallelize things and make it work. There's a limit to how useful that is, and eventually you'll spend more time talking between the nodes than actually moving the simulation forward. So far I've talked about gravitational simulations. I think that's it, right? Like the bouncing ball is because gravity pulls it towards the earth and then it collides. Gravitational interaction, right? In galaxies where you're modeling stars as particles, you usually just you measure the potential fields, you calculate an acceleration from that, you move all the particles. But simulations will be much, much more complicated than that. Oftentimes, you are modeling a gas, right? And a gas does not just interact like gravitationally, right? Like gas will collide with each other. There's heat exchange, there's chemical reactions. If you're thinking PV equals nRT, your gas at a really high pressure or really high temperature will become ionized, which means you now have moving charged particles, which means you also have to model magnetic fields, which means you need Maxwell's equations inside your simulation, tracking the movement of particles, tracking the chemical energy, tracking the energy trapped in the magnetic field. It just becomes a million times more complicated. So I showed you my little code that was like 4 lines to simulate a bouncing ball, right? I thought I would show you a real physics code software. The one I have right now is it's called Agama. It's a galactic dynamics code. So here's the code. This is what it looks like. If I just go to like the object files, this is how many codes, little modules are in here to make this thing work. So these are a lot more complicated than just writing like a little Python script. You have all of these different algorithms that work together. So you'll have a code that sets up your gravitational potential calculation, and then you will have a set of codes that do your chemistry routine, and you'll have a set of codes that like accelerate your particles, and you'll have a set of codes that write output files and data files and time step files and 100 more things. And all of these codes will be built to work together so that you set up an initial problem and you give it instructions on like what equations you want to use and what time step you want to use, and then all of these things, thousands of lines of code, work together to move your simulation forward and print output files so that you can like make beautiful movies and things from the data. It's a very complicated system, and it's a huge field of research because these things get more accurate, they get more realistic, they have higher fidelity, and they start working faster because people get better at writing code. And I don't know. That's computational physics. So in the simplest terms, computational physics is just making a toy model of a problem and evolving it in time, so you can look at its evolution and study its evolution. And so what people will actually do is they will run a simulation suite. So they might make 20 little modifications to their toy model and see how that changes the results. Or they might do like a Monte Carlo type simulation, like the people who run 1,000 models of the solar system and say like, oh, 3% of the time Mercury gets kicked out. You run a bunch of different, like slightly different initial conditions, you move them all forward, and you see how the results change. And you can't do that analytically. You can't sit down and with your pen and paper calculate how stars will move. You can't calculate the gravitational potential of individual stars. You cannot do this without a computer. The computer is required. And then whenever you think about like chaotic dynamics and how you will get a different answer every time because chaos actually changes how the systems interact with each other, which limits their predictive power. You can't do it, without a computer. So the computer becomes a necessary tool in solving these problems that are much more complicated. Like, yeah, in the 60s and 70s, people were trying to solve like galactic dynamics with these really simplified, beautiful like toy models. But if you want to actually look at what happens in galaxies, you need to look at 100 billion stars in a galaxy, and it's impossible to do it on paper. So that's where the simulations come in. Did I end up saying simulations were theory? In my opinion, simulations are firmly in theory. I think I'm back to that. That's where I think I'm back at, because it's just doing math with a computer that you can't do with your hands. A lot of experimentalists will do simulations just because it's cheaper to ask a computer what's going to happen than to test something and like burn your equipment and do all that. Oh my gosh, my voice, it's hot. My voice is crazy. I feel like I've been talking for a super long time. But I want to talk about one more thing, and I would never do this on my main channel, but philosophically, there are implications from simulations. So, I'm so very uncomfortable with philosophy, but I feel like it's important to mention. If someone throws a football to you, you're not doing math, right? You're not doing kinematic equations and like trajectory mapping. You just know intuitively where the ball's going to go and you catch the ball, right? The ball is also not doing math, right? Isn't that weird? It might not be weird for you, it's weird for me. The ball is instantaneously measuring the gravitational potential field it's in, and it is moving accordingly. And it's not doing any math. It doesn't know what gravity is. It's a ball. It's not sentient. And yet, like the laws of physics that govern the world happen whether we know about them or not, right? A simulation is our attempt at simulating those laws of physics, but we can't actually do that, because we're not actually, there's a limit to what we're doing because of that time step. Time in simulations doesn't exist, right? Like you have a ball, you say, okay, if the ball travels at that velocity for 0.01 second, where would it be? Oh, it's right here. Okay, recalculate what its velocity is. Now where would it be in 0.01 second? Oh, it's over here. But we're just picking the particle up and moving it. It is not moving that way. Do you know what I mean? Of course, you can lower your time step until it looks like it is, but it's not really. Am I talking any sense? I don't know. This is why I don't do philosophy. So here's the thing. In real life, time exists. In real life, the ball is moving and calculating its position in the gravitational potential field and moving accordingly, isn't it? Because we do have a time step in the world, in the universe. It's the Planck time step. It's the smallest amount of time. We have these devices that measure time, but we can't reach that smallest time step. We don't know if that's actually the smallest amount of time. Is it even possible for us to be able to measure that small amount of time? It's a very complicated question. I've been thinking a lot about this because I want to do like a concept of time video. But it's just, there's this discongruous comparison where in the world we experience physics, we experience the laws of physics, we experience time. But the simulation doesn't do any of that. The simulation is barely even a facsimile of what's actually happening, because we stop, we calculate, we move forward, we stop, we calculate. And that's, a simulation could never be real life. These two things could never, like, we could never make an accurate simulation of the world. That's impossible. There's no time in simulations. The way simulations behave model the world, but not even close to perfectly. And it could never do that. We could never run a simulation that has the small time step that we think we have in the world. Yeah. Anyway, I always think about that whenever there's like the physics, like the fake physics, quantum idea about how like we wouldn't know if we were living in a simulation. And that's such a useless thing to say or even think about. I don't know. So yeah, that's my philosophy nugget of the day. I sometimes think about like how like time exists in the world. It doesn't exist in simulations. How would you model it in a simulation? Which just opens questions to like, what is time? Anyway, I don't know. Did this video make sense? We walked through a simulation. I talked about some of the hard parts of simulations, and then I talked about how I don't really understand time. However, Windows machines. I almost forgot to talk about Windows machines. So the reason I hate Windows machines is because I hate Windows and I hate Bill Gates and all of its garbage to like make you angry. Like, you buy a new computer and it's just full of ads. Like, there are ads in Windows and there's nothing you can do about it. And that's garbage to me. The only reason I bought this Windows machine was because I'm doing a coffee video, and I bought like a little data acquisition like thermocouple thing, and so I'm measuring the temperature of my coffee every day, and that's been fun. But like it only works on Windows, and like, yeah, I could have written my own thing in LabVIEW, but like that would have taken forever. So I'm just using the Windows version, and it sucks. Like, the Windows as a whole just sucks. Like, it's shitty, it's full of bloatware, it's full of ads. Like, I bought a brand new computer and it tried to force me to make an online account, like an online Windows account, like before I would move forward. And I had to spend like 18 minutes just clicking enter before it let me onto the computer I had just purchased. And it's insane. It's offensive. I know I have an Apple account, and when I buy a new Mac, I log on to my little account. But for some reason, I was just so annoyed at Microsoft, because like, at least you can use your MacBook without putting in your Apple info. You can't even, it barely let me on the computer, and there's ads all over it. Like, I would rather not have a computer than have ads all over it. I don't know. I am so beyond, like, I'm just like, fine, I'll never watch Netflix again. That's where I'm at right now. I don't know, but they make it really hard to run software on your computer. In fact, I went to Best Buy when I was buying this computer, and they have a special version of Windows called like S Mode or something, where they won't let you install anything unless you install it through the Windows Store. Like you can't install things on your own computer without permission from, it's insane. But I was like a Linux person, and then I started grad school, and my first advisor was like, everyone in astronomy uses an Apple because all of the software is Unix based. So I could have still used like my Linux machine and the software, but I was just like, I need a new laptop, I'll just try a Mac. And you know, the thing about Macs is 10 years ago, when I bought my first Mac, it was like $3,000. And I was like, oh my God, this is so expensive, but at least it just works, right? And that at the time was like, oh, that's kind of stupid, because you go buy your Dell laptop 10 years ago and it does just work and it's fine. But now that comparison's no longer there, right? Like, you buy a MacBook and it's $3,000, but it just works. And my 10-year-old MacBook still works, you know. But if you go today and you buy, as I've just found out, a Windows machine, it doesn't just work, because you have to spend 2 weeks like taking the Facebook app off and taking the Amazon app off and getting rid of all the AI being garbage all over it. And it's just, the MacBook just works. That's why I'm a Mac person now. But I don't know in the future. Like, I don't know where this is going. Like, I know I'm never going to buy a Windows machine again. Like, never, ever. Just never. I'm never going to do that. And Macs, they are getting more expensive. So, like, I guess I'm going to go back to, like, Linux. And, like, maybe even buying, like, my own components, building a computer, and installing, like, a little basic Linux browser so I can just read the internet. I don't know. I don't know where this is going. That's all I have to say. Like, the reason I don't like Windows is because I don't like Bill Gates. I don't like him forcing my hand. When you use Outlook email, it doesn't search what you ask it to search for. It searches what you think you want it to search for. And it's like they don't think humans are capable of using or understanding computers. And that's why I don't like Windows and would never use it. Yeah. I'm probably going to edit that whole thing. I don't know what's going on there. Okay. I don't know what I'm working on. I put out that video about that dark matter video, and I kind of think it would be funny if that was just like my last ever video. I don't know. I've been watching Star Trek Picard. I might talk about that. I've been wanting to debunk astrology for some reason. I don't know. It's the summertime. I always feel like I just lose any and all motivation to do anything in the summertime. I hope you guys have a good summer. Are you going on vacation? Anybody doing a vacation? Should I go on vacation? Let me know in the comments below. Anyway, thank you so much for your support this month. Also, I have switched up my camera, so I don't know if I'm looking. Am I looking at you? Is there or there? Let me know how this is. Does it look better? My last video ended up being in 720p, and I don't know if I exported it incorrectly or what. I think it was the filming setup, so I think this is better. We'll see. Let me know. Have a good month, and I will see you in July. All right, bye.